In this Tobacco University video, I'm going to walk you through heat calculations and different formulas to utilize to work through these calculations. So if you grab a pen and paper, you can work through some of the problems as I go through them here in this video. All right, so this is a reference table that you may need to refer to for some of the questions. We're looking at different substances, heat of fusion, melting or freezing, heat of vaporization, and boiling or condensation point. So these would be given values. It's now how do you utilize these reference values to apply to the equations that I'm about to go over. So first off, we have different heat calculations. We're going to use these three are going to be the main focus. The first one we're going to use when temperature changes only when one phase is present. Second one is during the melting or freezing phase. And the third one here is during the vaporization or condensation phase. So the F you can think of freezing, the V for vaporization, and this is when only one phase would be present. So let's go through some examples here. So we're looking at our heat calculations. Q equals M times C times delta T. This is used when temperature changes only when one phase is present. As a reminder, for specific heat of water, use that table B, or that first table that I provided you with in that second slide there. Example, so what is the change in heat energy when 40 grams of water at 25.0 degrees Celsius is raised to 60.0 degrees Celsius? So again, we're looking at our heat, our mass, our specific heat, and our change in temperature. Now we've got our temperature change here. The specific heat is given to you on that reference table. We've got our mass provided, so we're simply calculating for Q in this case. Looking at the heat of fusion calculations, so just to give you a kind of a rundown of here, when we're using this during melting or freezing, you want to look at the reference table. We're looking at water in this case. The heat of fusion is 334 joules per gram. An example would be how many joules are required to melt 250 grams of ice at 0 degrees Celsius. So I'm going to go through this one on the next slide, but again, something very similar. Q is the heat energy, M is the mass, and H subscript F is the heat of fusion. So again, how much heat is released when 250 grams of water changes to ice at 0 degrees Celsius, and how much heat is needed to change 75 grams of ice at 0 degrees Celsius to a liquid at the same temperature. So we've got temperature involved here. We've got our reference table on that second slide there to take a look at. We've got our calculation steps. So if you want to take a moment to go through and do some calculations, pause the video here before I reveal the answers. All right, so hopefully you kind of had a chance there to kind of go over, figure out your answers, and hopefully you got 83,500 joules for the first one, 25,050 joules for the second one. If you did not, go back to that equation, write it out, keep track of your units, keep track of your variables, and hopefully you can find out if you made an error where that error actually was. Now looking at heat of vaporization, again, Q equals M times HV. This is during the vaporization or condensation process. Here, the reference table for water, we're using a difference reference value because we're looking at the vaporization number, which would be 2,260 joules per gram. So we get an example of how many joules of energy required to vaporize 423 grams of water at 100 degrees Celsius at 1 atmosphere. In this case, I'm giving you the pressure here just to ensure we're kind of at that sea level, essentially. So here I've got three different examples, three different questions that you can kind of work through. Again, how much heat must be supplied to evaporate 50 grams of water? That one I just gave you here is how many joules of energy are required to vaporize 423 grams of water at 100 degrees Celsius at 1 atmosphere. And if you're feeling really confident, go through and calculate how much heat is required to evaporate 150 grams of a substance at its boiling point if it has an HV heat of vaporization of 987 joules per gram. So giving you just kind of examples of giving you different portions of that same equation, still having one unknown. You have to go through and rework that equation to solve for the unknown. Take some time and do that for these three before I reveal the answers. All right, so let's go through and hopefully you got your three answers. And these are the three answers provided here. The first one, 113,000 joules. The second one, 955,980 joules. And the last one, 148,050 joules. Now these heat curves, again, here we can kind of see the equations as they relate to different portions within that phase change. And we've got those values of water. Again, we're just sticking with water here, pretty consistent, pretty common example. And we've got the kind of different values here that we can then go through and plug in. So it's realizing what portion of the phase change diagram you're at, what way you're going, and that directly correlates to what equation you would use and plug in those numbers to. So let's go through another practice problem here. A sample of 5 cubes of ice from my freezer melted and warmed until the water is 104 degrees Fahrenheit. My freezer compartment is at 0 degrees Fahrenheit, and the cubes of ice are 25 grams each. Calculate the amount of heat to do this. Let's go through this kind of basic process here. Again, we're going from a freezer temperature, 0 degrees Fahrenheit, all the way up to 104 degrees Fahrenheit. So what's our first step here? Well, if you notice, the units given are in Fahrenheit. So you have to change those temperature units to Celsius. And here's a little conversion factor. Here's some examples as well. So you can plug in those Fahrenheit numbers, and then we can go through and calculate them in degrees Celsius. So 0 degrees Fahrenheit is minus 17 degrees Celsius, and 104 Fahrenheit is 40 degrees Celsius. So if we continue here, after we do our temperature calculations, we have to map out the regions and at temperatures on the heating curve. This is your map for the problem. Again, we're starting at minus 17 degrees Celsius. We're going to warm up, plateau for a little bit, and then warm up again. So these are going to be 3 regions that we're going to have to calculate. We have to calculate these 3, where these 3 green arrows are. We have to calculate each of those steps to get the final sum total. So after we go through that, to do calculations for each step, well, we were given the grams of ice, because again, it was 5 cubes here at 25 grams each. We've got 125 grams of ice essentially, and we're plugging in our different values here. Again, the mass is going to stay consistent. Our heat of fusion, our temperature of the water, and our givens, our knowns, are all going to change. So that's what we're plugging in. And we're calculating the joules for each of those different heating curve steps. So here's a kind of a zoom in here. Once we calculate them all, the step number 4 would be to sum the steps and convert it to kilojoules. The reason why we're converting this to kilojoules, it's a fairly large number. 67,111 is simply converted to 67.1 kilojoules. So we can see if we put that all together, this is kind of what the entire practice problem would look like. This would be the most complicated problem because it is involving multiple steps there to then go through and add. But I think if you're comfortable with the first few problems and look at this one, you're able to break it down and understand what phase changes are occurring, what equations to utilize. Hopefully, looking back and going through this example, it's not as difficult as it may have seemed at the beginning of this video.